Here we go. So the idea for today is, we're just going to continue with what we started last time. Let me be sure everything is recording as it should. Yeah, I think we're fine. So remember we have office hours today after lecture at 12:20. What I want to say today for the first couple of minutes, let me grab this one. So so the idea, maybe let's start with what I actually want to discuss today. Today we're going to discuss bases, and if we have time, subbases. So this is chapter 13 on the textbook. What we did last time, before we start this, so last time, essentially we introduced what a topology is. So topology on a set X. And this is some collection of subsets. And we want three things out of this collection. First one is the two trivial subsets are in this collection. The second one is, let's just say, arbitrary unions. So this collection should be closed under arbitrary unions. And the third one is closed under finite intersections. So that's what a topology is. And we were trying to convince ourselves that this was a useful notation. I think we did that with the standard topology of the real numbers. So hopefully you agree. One nice example here. This was kind of weird, but let's call this our standard. So this should be reals with standard topology. So here the topology was defined as, I'm going to consider all things inside the reals, for which whenever you have an element in the set, you can be sure there is some epsilon, such that the entire open interval is inside that set that you have, which was kind of weird. But today we are going to continue with this idea. I wanted to remember this. So this should be called the standard topology of the reals. Remember, verifying this was a topology was rather easy. Cumbersome definition, not so easy to verify. It's not so hard to verify it's a topology. So before we dive into more sophisticated things, let me say something I wanted to mention last time. Definition one for today is, this is like a naive way, this is like a naive version of how do we compare topologies. It's very naive. So this is going to be two topologies on the same set. So let's take T1, T2 topologies on the same set X. And we're going to say, maybe let's say, in case T1 is a subset of T2, so this means whatever is open regarding to T1 is open also regarding T2. In this case, we say that T1 is coarser than T2, and that T2 is finer than T1. So what do we mean by this is, well, topologies in some sense could be thought as filters. And if you think in those terms, here you're saying your filter is finer. So to be completely honest, I'll usually go with this one. I'll say something is finer than something else. And if one of these, so if either, so that's the first definition, and if either T1 is a subset of T2 or the other way around, we say that we can compare these two, because that's not always going to be the case, right? Have two topologies, it's not necessarily true that one is a subset of the other, but if it happens, we say we can compare them. So we say T1 and T2 are comparable. So to be completely honest, not the most interesting nor exciting definition, but I wanted to know this. And some kind of easy examples would be maybe example one. If you have a set X, any set, you can take, for example, the trivial topology. So, the trivial topology. So this is the topology where we are only having these two sets, MT and X. So this is what I called T-triv. This one is a subset of any other topology because of what? So this one is coarser than any other topology. On X. Yep.
So it's coarser because it can contain every topology, like the trivial topology.
It's contained. And then, of course, the discrete one on the set and the discrete and tau discrete, which is the entire power set, is finer than everything else. So it's finer than any other. Yeah, but I want to say, like, these are the two trivial or the two topologies that you always have, like, for free. So I want to include these two on the same example. Any questions about this? So just as an exercise for you, to be sure you follow what's going on here, maybe I want to keep this Blackboard new for me. So let me use this space over here. Oh, what's happened with this? Yep.
Quick clarification for the power set. You're saying that's finer than every topology because I guess I'm a little confused because isn't the definition of topology you're taking a subset of the power set, but here you're taking the whole power set. And you're saying that that can be a subset of any topology that you take, right?
Oh, finer means contains.
Okay.
Finer means you contain every other thing.
Trivial one is coarser, but it will be contained.
So exercise for you to remember or for you to do something about this. On the reals, let's say the confining topology, maybe let's just leave this as a question. Can we are we able to compare the topologies R standard and R cofinite? Are these two guys comparable? So This is a good question for you. Are these two topologies comparable? Have two topologies on the same set. Here, in our standard, opens are unions of intervals. And here, kind of a hint, but this is just a definition. In confinite topology for the reals, opens look like the entire set minus some finite number of points, x1, blah, 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 xn. So the question is this guy union of open intervals? So that's a question for you. Okay, any questions about this?
I think the book also said you can use the words larger and smaller.
Yeah.
So larger here is higher.
But there are two versions of that, even the textbook.
Yeah, they have strong and weak.
If you ask me here, T2, so the one that's bigger as a set should be larger. And that's what the textbook also says. But the thing is, some people use this larger in the complete opposite scenario for some weird reason. So yeah, because you could say, yeah, larger as a filter, you're larger.
I guess say finer, it means you have more details.
If you exactly
counts.
Exactly, you have more resolution.
Yeah.
That's why you go with finer. Okay, so now let's go with what I want to discuss today: basis and subbasis. So this is actually new stuff. So the idea here is something like, in our examples, usually what you do for topology, we don't have that many examples, to be honest. But usually what you do is you describe all open sets. Or you do something very smart like we did for the standard topology of the reals. So let's say, let's focus on basis first. The idea here is we want two things, which are sometimes very easy to confuse. We want to do two things. One thing would be describe topologies that we know. To be completely honest, we know the standard topology of the reals. We didn't know it as a topology, but we knew it. So here we're kind of describing it using that idea. But we also want to define topologies. And that's what we did with the standard topology for the reals. We defined it using that weird idea. But I want to make this distinction because it's very easy to get confused with this. And I'm going to start this topic from a different direction of what the textbook does, because I'm not so comfortable with what's going on over there. So what I'm going to do now is a base is going to be some subset of a topology. So base, the idea for base is going to be something like general version, or we should generalize this collection of all these open balls, all of them. So X should be any real, epsilon should be any radius. So it's going to be a collection of sets. Now, I want to describe that set on a very different but more concrete way. And that's going to be our first result. So let's call this a lamp. I'm going to start with the set, let X be any set. And I'm going to take B to be any collection of sets. Some family of sets. Now what I want to claim is we have an equality of sets as follows. So on one hand, you can take all subsets of X which you can make using elements in B by unions. So some arbitrary unions so I'm taking here things that you can obtain as unions of some elements in B. And this is an arbitrary index set. So this set I'm claiming is going to be equal to that sort of thing. Subsets of X for which whenever you have some element in U, you can always cook up some set on what's going to be our base, for which you have something like this. So remember, the picture here is something like here's your U. So here's your U. Whenever you pick an X, you should be able to find your B. That's inside of U and contains X. But this B needs to be in the prescribed family. So B is not anything, it's something in the prescribed family. So here's part 2. This is how we describe part 2, what you should think about this. And these things are just unions of sets in B. So I really like this lemma because it's something like, seems kind of nonsense, but what's actually going on here is this is somehow describing U globally. So I'm telling you what U is, and here I'm describing U what's called locally. For each element in U, I'm telling you something about it. But these two sets are the same. So you can either describe it globally or locally. And that's for any collection B of subsets. Yeah.
You have to define B. All we said is that there will be a B that's a subset of U in relation to X, and then you wrote through as like a circle around B. But how do we define the length of B, or like how large B is, right? As a subset.
Yes. So I'm just saying here, these two sets are the same. That's all I'm saying. I'm not finding anything. I'm just saying these two things are the same. And sadly, I don't have enough space, but this is the important part. These two sets are the same. Yep.
Does there have to be a finite number of B?
No.
No.
So very general. Okay, let's go with the proof now. And maybe let's say we denote this common set by tau of B. Because the idea is that things should be a topology. That's not going to be always the case, but that's what's behind this. Okay, now let me delete this motivation over here so that I can have a proof close to our statement. So here's the proof. So I need to show two sets are the same. Seems cumbersome, but usually that's just element tracing. So let's go with, for example, this inclusion. And I usually refer to this as global description, local description. So let's say this is global. I'm describing U globally, and here I'm describing it locally.
The second one.
The second one is local, and the first one is global. And one I'm describing the set, and the other one I'm saying something about the elements of the set. So proof, let's show global inside local. So here we need to take some set U on the, what should be like the right-hand side, like the first one. So I need to take U as a union over some arbitrary index set, where all BIs are in B. For all I. And now I want to show U is an element on this family here. How do we verify that? We need to take an arbitrary element of U and do something about it. So let's take an arbitrary X in U. Not going to be very complicated. We want to show that U is in some basic set, some element in that B, for which we have this inclusion. But our U is just union of a bunch of these guys. Right? So if we take an X in U, then it's just going to be an element of some BI, and then that BI is an element of the union, it's a subset of the union, sorry, and then we're done. Right? So since we use this union of the PIs, we have X as an element of some Bj for some fixed J. And then X is in that Bj, which is a subset of the union of all BIs, which is our U. And of course, this guy is an element of B. And then we're done. Is this clear? Yep.
Okay, so can you reiterate? So, okay, so we're taking, so we want to prove this inclusion. We're taking an arbitrary element of U, and then we're saying that, how can we say we have it in Bj?
Well, because U is just a union of BIs.
J is some arbitrary I, right? Like, there's no
Well, not really arbitrary, it depends on X. For that X, there is some J such that X is in Bj. And then for that one, we know this, and then we're done because we just want to show this, right? X is in some B inside of U, and it's on some B inside of U. The important thing is that prescribed B is in your basic set. Okay, then we're done. Now, other inclusion. So here we need to go from local to global. So let's assume we have some U in, I don't want to write this. Let's assume we have some U in local. So we have U satisfying this. And now we want to show our U is going to be some union over some index sets of some BIs, where each BI should be an element of our basic set Bx, B for all I. So what's the idea here? The idea is, let's go to the local description. We assume our U has this property. We want to show U is union of BIs. The thing is, for any point here, or any point in U, you can always have a ball. Take the union of all the balls, that will be your U. Can't be anything else. Yep.
This is a quick clarifying question, kind of also related to the previous direction, but so we can say that X is in, there will be a B such that X is in the inclusion, because at some point, we know that B is a subset of U, and at some point it could just be all of X, right?
No, that's definition of union.
Oh,
U is union of things, then an element here is on some of the sets. Nothing deep.
that U is a subset of X, and we know that X is an element in U, right?
No, U is not a subset of X. So this X is an element of, it's not capital X. It's not the set X. It's some element of X.
Okay. Oh, wait, sorry, we know that X is in U.
So this X is not this X.
No, I think it's little x is in U, right? That's of U.
Uh-huh.
And U is a subset of big X.
Uh-huh.
Then X also must be in big X, right?
Oh, yeah.
Okay, so one thing is, the reason we know that X, that if, that there will be some B sub J such that X is in there is because at some point the B sub J could be the entire union, right? So,
No, it's because it's definition of union.
oh, okay, I see. So there will be, yeah, there will be if X is in U and U is defined by this definition, right? Then there will be a J for which X, there has to be a J for which X will be in this B sub J, okay?
Okay, so now let's go back again. We're assuming U has this local property. We want to show it has that global property. Namely, we can write it as a union of elements in B. So how do we do such thing? Once again, we have this property for each X in U, we have a ball. So this is the picture. You take all possible balls, what you will have is U. Right? Each ball is contained in U, so the union will be contained in U, but each element of U is inside some ball, so the equality will hold. So let's write that. We want to show this. Now we want to use our local property. So for each small x in U, we know there is some Bx, let's call it, element in B. I'm using Bx because it depends on X, for which we have that. X is an element of Bx, which is inside of U. So for each X, we have this small Bx, kind of neighborhood. And now what we should claim, we claim that if you take the union of all these Bx's, where X runs over any element of U, you should have the entire set. Right? Two inclusions are clear. Each Bx is a subset of U, so the union is a subset of U. And if you take an arbitrary element in U, then it lives inside Bx, so it lives inside the union. Yeah.
This kind of, I know it's not, but when I look at it, I'm kind of confused because this seems like circular reasoning to the previous problem, where the previous problem we say, let there be some, right, like B sub J, and then that's a subset. Here we say the opposite, right? We say,
yeah,
let there be some B sub X that's already.
Yeah, it's the converse inclusion. Yeah. Okay, so we claim this equality of sets. How do we prove it? So we need to prove two things. If we want to prove this, if you take an arbitrary y in U, then we know it's an element of some Bx. It's the element of By. So you take your y, it's inside By. Then y is in By. Then it's also in the union, because By is a subset of the union over all X in U of Bx. So that inclusion is for free. The other inclusion is even easier. Each Bx is a subset of U, then also the union. This inclusion is even easier. Each Bx is a subset of U, then also the union. Each Bx inside of U, then also their union. So that proves this inclusion. So U satisfies global. And we're done. Yep.
Just to clarify, so we can say that Y is in B sub Y, and that is contained in the union of Bx, because we've already proven that that is just the union, right?
No, because By is one of these guys.
So By is the net.
So yeah, this union is By plus some extra B's.
Also, we had to do a bidirectional instead of the second direction.
Right, so here we're proving two inclusions of this.
Yeah, and then U is and also the union of
Mhm.
BX, and then an element of BX, the union of BX is in U.
Yeah, but for the second inclusion, I'm not going like element chasing. I'm just using like basic set theory arguments. Okay, any questions about this?
That had nothing, those are both open sets, right? Or did we not know that?
There's no topology here, just sets. I don't like this. Yeah, there's no topology so far.
That-
Weirdly enough,
Those could be open or closed, and that would be fine.
we don't know. There's no topology. This is very general stuff. Now we'll do something about it, of course, but there's no topology so far. And that's pretty much the point of this. Okay, let me move to this whiteboard. Yeah. Well, kind of, but it's mostly like generating sets. There's no like independent. Yeah. Yeah, the T of B describes any of these two expressions for this set because we know they're the same. So if you think of like this, you're saying any element in the B set here is a union of things in B. In some sense, like a generating set, and that's how we're going to call this. But it's not really a basis in the linear algebra sense. So that's our definition. Definition for today will be number 3. So now let's assume we have a topological space, X tau. I want to emphasize tau here, or T. So we have a topological space. And let's assume we have some set B inside of some collection of sets. And we're going to define exactly that. So we say that this B is a basis for T if this T that we have coincides with TB we defined before. With this TB over here. So what this means is open sets are exactly things that you can write as unions of sets in B. So the collection of all unions that you can form using sets in B in this blackboard bold B, that's your topology.
What is tau if? Let's say tau if. Oh, that's just like a word in. Okay.
Yeah,
It's not a
it's
set.
T if, or maybe let's say 1. So that's what we're saying. And in this case, we also say that our set B generates the topology that's given, T. That's a given topology. And of course, notice here, T of B only depends on B. Right? So B cannot generate more than one topology. Because only depends on this set only depends on B. Right? So if your B generates 2 topologies, then they need to be the same. Both equal T of B, then they're both the same. So examples here. First one, I will usually try to use our trivial examples and our trivial example and our discrete example. So discrete topology. So remember here, everything is open. So discrete topology on a set X, this will have the basis given by the collection of singletons, where X is any element of X. Right? What's an open set in this topology? Any subset. And any subset you can write as an arbitrary union of singletons. Which singletons were exactly those labeled by the elements in your set. So that's the discrete example, and the trivial. And this is something I want to mention at least once, because it's sort of a convention. So the trivial topology, remember, is only the trivial, the empty set and the entire set. So the trivial subsets, trivial topology, the basis here will be just the entire set. Because I want to mention this, by convention, we assume that the empty set is always a union of some collection of sets, namely the empty collection. So this is union of empty collection. So what I mean by this is my TB here, where is it here? Maybe because of this, it always includes the empty set, because I assume the empty is the union over the empty family. It's just a convention. Okay, any questions? Yep.
So the basis will always be defined as a union of sets. So it just gets emphasized like that.
The basis, well, the basis is not something that you define. The basis is something. Well, but in this case, it's like I'm computing. It's not unique. That's what I mean. You could have like more bases. For example, that's one basis, but then I could also take like singletons, where X is an element of X, and then maybe I can also take sets with two elements. That's also going to be a basis. In fact, if you have a basis and you start adding stuff, you will always have a basis. That's very, very different from linear algebra. But once you have a basis, you can like add more stuff and you still have a basis. Right? So it's not really something that you compute, but something like you try to find. It's an easier way to describe your topology. Well, here in the discrete, an open set is any subset. And any subset is always a union of some of these guys. Right? Because if you have any set, let's call it Y is always the union of the singletons, let's use A, where A is an element of Y. We allow arbitrary union, so that's perfectly fine. Yeah.
So I guess is that similar to in a cyclic group, the element that generates that group? Like, so the basis would be kind of like that.
Yes, but yes, maybe. No, you don't need a cyclic group. You just need something that's generated by something. Yeah, but what you should try to. So yeah, once again, the idea here is this basis business. What it's trying to do is either describe in easier terms a topology that you have, or define a topology. But it's not as useful as you're used to when you hear the word basis. It's not linear algebra. It's definitely not linear algebra. In linear algebra, a vector space is completely determined by basis. Here that's true, but not completely. It's like you can do weird things with basis. Okay, so yeah, now let's do an interesting example. So example, so for us, we have the standard topology in the real numbers, right? So here, this is the reals with the standard topology. And remember, by definition, T standard is subsets of the reals for which whenever you have an element in that set, you can always find an epsilon for which the ball is inside of you. Right? So this is, by definition of the standard topology, this is what we're calling T of B, using our local description of T of B, where B is the collection of balls. So all balls, X epsilon, where X is a real, epsilon is a positive number. So this is exactly the local description of T of B. So when we define the standard topology, we use this T of B. Are we okay with this? Now I want to be like more, even more precise with local versus global. So here, this is local because it's like fixed on some X and you're taking a radius. But remember, this is just the interval X minus epsilon, X plus epsilon. And my question is that interval any special interval? X minus epsilon, X plus epsilon? That's just an open interval. Any open interval looks like that, right? So B is this, but it's also the collection of all intervals A, B, where A is smaller than B. Right? So here, if you go from one to the other, if you have this interval, then your X should be the average of A and B, A plus B over 2, and then your epsilon should be, well, B minus A over 2. That's what I'm saying. So this is not a restrictive interval, that's any interval. But here, we're putting the emphasis on the middle point, and here we're just saying, well, this is any open interval. So open intervals are basis for the standard topology. That's what I want to say. Open intervals are a basis for the standard topology. And this is really telling you like this global versus local. Any open set is a union of open intervals. In other words, any open set is something such that whenever you have a point, you have an interval like this inside that set. Same thing. Okay, so the thing is, so far we've used this basis business to, I'll say, mostly describe topologies, because this we already knew. This is we're defining this topology, but it's something we already knew. Like open intervals, it's something we already knew. And now the opens are unions of these guys. But now what I want to do is, the next question is, the question here, what I'm trying to answer is, define topologies, define T using B. So this is what I'm trying to do. And the question is, given a set, B inside the power set, when is this guy a topology? TB a topology. Remember, there is no topological concept beyond behind the definition of T of B. It's just union of elements in B. That's the global version. Yeah.
What's the last two words like?
Oh, for the, yeah, sorry. So it's a basis for the standard topology. Yeah, sorry about that.
Quick question on notation. You say given B, I'm trying to follow when you write B without two lines and you write two lines.
So this should be, I'm trying to do like a curly B or something, but that's too much for me. So I'm doing the math BB version. It's usually called like, usually I use regular B for an element in the basis. Yeah. So this is math BB of B. And I would like to be able to do math cal of B, but I cannot.
Yeah.
That's what's going on. Okay, so that's the question. When is T of B a topology? Because it seems to be a very nice thing, right? It's a very nice description of a topology. For example, here, open intervals are basis for the standard topology. Okay, but that's good because open intervals have some properties. So can we impose some restrictions on B such that T of B is going to be a topology? And that's probably the main result for today. So this will be proposition 4. Am I recording what I'm supposed to? I don't think so. That's bad. Sorry about that. So zoom out a bit. Now things should be better. Yeah. So proposition, I think it's number 4. So now again, let's take a set. X be a set, so I don't need all this nonsense. Let's X be a set, and let's take some family of subsets. And the answer, we're just going to answer that question. Then T of B is a topology on X if and only if 2 things. The first one is kind of innocent. It's kind of X is in T of B. So X is the union of all elements in B. So that's kind of the trivial one. And remember here, I don't need to say anything about the empty set because that's always my convention. Just take the union over the empty family. And the second one, this is kind of the local version. Whenever you have 2 elements in B, B1, B2, I want to. So T of B is collection of all unions. So unions should be okay. The problem here is intersection. How do we deal with that? Whenever you have 2 things in B, the basic set, and whenever you have any element in the intersection, because that's the thing that's problematic, you can always find the third one containing X. There exists some new B containing X. So something like X is in B, which is a subset of the intersection. And this was the crucial property of open balls in the reals. So we have something like B1, B2, B1, B2. The intersection property is if you have an X in the intersection, you can always have a new ball here. So this is your B. And makes complete sense. Unions should be for free. Intersection, you need to say something. The something we are saying is exactly what we said for open balls or open balls in the reals. Any questions? Yeah.
Notation 1.
Uh-huh.
You say that X equals the union of big B in the set. But you use B as the index. So we're not the index of what you're taking the union of. So
Well, here I'm not indexing things.
yeah, but you're saying B, right? B on the underneath side of it, and then on the side you're saying B. So You're just saying the union of any arbitrary B, right? That's gonna equal, of all of them, that's gonna equal.
I'm taking the union over all subsets in this prescribed family. So that's our proposition. We need to prove it now. If and only if, so we need to prove two things. And that's pretty much telling you for the collection of unions of elements of B, that's what T of B is. For that to be a topology, it just need to be able to verify the intersection property. Like the second one over there. It's kind of a local intersection property. And of course, here I will need to use the local and the global description of T of B. So let's maybe go that direction first. So we assume T of B is a topology. And we need to show 1 and 2, right? So to prove 1, we don't need to do much. So to prove 1, to prove, let's say 1, how do we go about that? Well, since this guy is a topology on X, since T of B is a topology, X is open. So we have, under any topology, we know that X needs to be in T of B. Because we're saying T of B is topology. And then this means, by the global description, let me say I'm using the global description of T of B. We have two different ways of looking at T of B. Hence, by global, we know that X is going to be the union of some BIs. The union of some BIs. For some BIs. In B. But if it's the union of some, then it's the union of all of them. Because everything is a subset of X here. We just throw more stuff in this, and we're okay. So I can just take all this. Adding more stuff because everything is a subset of X. So here, the important part is not that it's a union of everything in B, it's the union of some stuff in B, in the basic, in the base. So that's for part 1. Now part 2, that's where the work should be. So part 2 here. To prove part 2. Here we're going to use the local description of T of B. So let's take two elements in our basis, B1, B2. And let's take something in the intersection. So what do we do about this? What can we do? We're assuming T of B is a topology, right? These two guys are in B, so also in T of B. This is just the most easy union that you can have, just union of one element. So these two guys are open. Then also the intersection is open, right? So since B is a subset of T of B, and T of B is a topology, that's what we're assuming. I don't know that the intersection is going to be in B. That's pretty much never the case. I don't know that the intersection is going to be in B, but I know it's in T of B. So since B is inside of T of B and T of B is a topology, we know that the intersection B1 intersects B2 is in T of B. And that means only one thing. That means B1 intersects B2 is not an element of B, but the union of those. So that means our intersection is going to be union. Now I'm running into trouble because I can't use my indices. So maybe let's use what did I did here in my notes? Let's see if I can use the same notation. Oh, no, very easy. Very easy. Could I check my notes? What can we do now? I want to prove 2. And I was going to use T of B's topology. That's okay. But I can also use my local description of T of B. And I know that's true by the local description. Do you follow? We know this. Now by our lemma, by this guy, this is our T of B. The intersection is here. X is something here. So we know this. Then by lemma 2, maybe let's say by the local description, we're done. We're exactly done. 2 is true. This intersection is in T of B, then there exists some new B in our basis Blackboard B, such that our fixed X is in B is inside the union. And that's because B1 intersects B2 is in T of B. I'm just using this description. So here, instead of U, I can use B1 intersects B2. I can use B1 intersects B2. So the work was already done. That's why this lemma is so important. Are we okay? Yeah.
So when you said by the local description, okay, so you're saying, because the local description gives us that there exists,
Yeah, but sorry, maybe let me finish and then maybe you can ask. So that's the forward direction. Are we okay? That's forward direction. And then the backwards. Yeah, I will not be able to do that today. So let's stop here. I will do the backwards direction next time. So this needs to be continued, and we'll do the backwards direction next time. And yeah, let me stop the recording.